Okay, so today we are going to continue our discussion of modules. So what we want to do today is characterize kernels and cokernels in the category of R modules and talk about some of the properties they satisfy. In particular, these properties play into the category of R modules over a ring R being what's called an abelian category. So if we have an R module homomorphism phi that maps M onto N, the following properties hold in the category R mod, which is the category of R modules. Kernels and cokernels exist in R mod. Phi is a monomorphism if and only if the kernel phi is trivial, if and only if phi is injective as a set function. And lastly, phi is an epimorphism if and only if the cokernel of phi is trivial, if and only if phi is surjective as a set function. So we tend to take it for granted because most of our work happens in nice categories, like the category uh, of abelian groups and the category of R modules. We have this equivalence between um, being a monomorphism and being injective as a set function. Now, and equivalently, we have an equivalence between the phi being epimorphism and phi being surjective. So the statement of a monomorphism and epimorphism, which we'll review in a minute, that's a statement about properties of how the functions behave between objects. And the injectivity and surjectivity is just the way that we understand them classically in terms of sets in the category of sets. Now, the definition that, or the property that we're most familiar with is that if the kernel is trivial, then we're injective. And if we're injective, then the kernel is trivial. So and the same thing with the cokernel. If the cokernel is trivial, then phi is surjective as a set function. These are proofs that we've seen before. But we will show the more interesting stuff is that they're actually equivalent to being epimorphisms and monomorphisms. Um, there are categories in which there are functions or morphisms are epimorphisms, but they are not surjective. And equivalently, there are categories where there are morphisms that are monomorphisms, but they are also not injective. So this is actually a very special property satisfied by the category of R modules. So we will recall the definition of monomorphism and epimorphism. Um, so we have a mapping F onto M, F that maps M onto N. So we could just say M and N are sets, or they're just some um, objects in a category. And we say that this function is a monomorphism if for all mappings G and G prime that map P onto M, we have this equivalence condition that F composed with G, if F composed with G is equal to F composed with G prime, that implies that G is equal to G prime. So this is kind of equivalent in the category of sets. To having a quote unquote left inverse. It's not the same because F may not have a left inverse, but this is a statement that is essentially saying that we can quote unquote cancel on the left, and a mapping F that maps M onto N, we say that's an epimorphism if for all mappings H and H prime that map N onto Z, then H composed with F, if H composed with F is equal to H prime composed with F, that implies that H is equal to H prime as functions. So these are statements about how the functions behave um, without referring to elements, essentially, of the sets. We know that injectivity is a condition on the elements of the objects, right? So if we have sets, then we're injective if two elements that are equal, they get mapped to, or if we have the images of two elements, the images of two elements are the same, then they come from the same element in our domain. This is a condition that abstracts that and essentially captures the functional properties of what it means to be injective and what it means to be surjective. So it expands those kinds of definitions. Now, to say that kernels and cokernels exist, we mean that we are going to define them in such a way that they satisfy an appropriate universal property in some kind of ambient category, which we will break that down after we define the what the kernel and cokernel, what they are as sets. They will satisfy a certain universal property, um, and that universal property is that kernels will be initial objects and cokernels will be final objects in these ambient categories that we will define. Um, we'll make that more precise later, but first we'll define what the kernel and cokernel actually is. Now for the kernel, this is nothing new. The kernel is just the set of elements in the domain that map to 0 in the codomain. Um, that's the standard definition of the kernel. The cokernel um, is the image, right? So we're looking at the image of phi, and we're going to mod the codomain by the image of phi. Um, a nice way to think about this is that the kernel map and the kernel measures how injective a function is, and the cokernel measures essentially how surjective a function is. Um, so if the image of phi is equal to all of n, then the cokernel will be equal to 0 because n mod n would be just 0. Um, so that means that uh, if the cokernel is trivial, this is what we're going to prove, that the function is surjective, and equivalently for the kernel. Um, so these are kind of, you could think about them as measures of injectivity and surjectivity. There are other ways to think about them, but that's the way that I like to think about it. So we're going to start with the kernel. So we're going to define a category C whose objects are pairs, alpha, comma, p, where alpha maps P onto M. This is an R-modular homomorphism such that phi composed with alpha is equal to 0. So I think I have, okay, here. So essentially what we're saying is that, let's go back here. Essentially what we're saying is that we're going to have a category whose objects are pairs, right? So we have P, and we have M, and we have alpha. That maps P onto M. So essentially what we're saying is that these are our objects. These are our objects in C. And we also have the condition. So we remember we have this map phi that maps M onto N. So we have the condition that phi composed with alpha is equal to 0. So the objects are these guys, and we're always going to have this kind of ambient morphism. And we're always going to have this ambient morphism. So alpha, phi composed with alpha. So we have these two pieces of data, right? We have our object, our initial module, not initial. We have our module P, and we're giving, we have our module P, and we have a function from P into M such that phi composed with alpha is equal to 0. Okay, so what we're saying here is that that the image alpha of P, that's a subset of the kernel of phi. So all of P maps into the kernel of phi. Um, so that's the conditions that we have, and morphisms in this category, right? So if we have two objects, um, so we have morphisms in C. We have two objects, alpha 1 P P1 and alpha 2 P2, right? So these are our two objects. This guy right here, and this guy right here. So these are two objects, and both of these satisfy phi composed with alpha 1 is equal to the trivial morphism, and phi composed with alpha 2, that's equal to the trivial morphism as well. a morphism between these two objects, these pairs, is going to be a diagram. Okay, so what that means is that a morphism will be a diagram, specifically an R-module homomorphism that maps P1 into P2 such that the diagram commutes. Okay, so when we say that the diagram commutes, all that means is that if we go down, if we start at, let's say, P1 and we go through alpha, right? So that's saying that alpha 2 composed with beta, that's going to be equal to alpha 1. That's what it means for the diagram to commute. So those are morphisms in this category, and our claim is that, so we have this category, it's great, and we're going to look at the object. We're going to show that the object associated with the kernel of phi is in this category. So we're going to look at the pair J kernel of phi, right? So we know that the kernel of phi is a submodule, so particularly it is an R module, and J is the injection of the kernel of phi into M. So we have J that maps kernel of phi injecting into M. So this is going to be one of our object here, J kernel of phi. And as we see here, we can see that this object is indeed in the category. And to check that it's in the category, we need to show that phi composed with J is the trivial morphism. But J is just the injection of the kernel of phi into M, right? So if we start in the kernel of phi, so let's go over here. If we have some element A in the kernel of phi composed with J of A, well, that's just going to be J of A is the injection, so it's just going to send A to itself. So that's going to be phi of A, and since A is in the kernel of phi, that means that this is going to be 0. So we see that phi composed with J is the trivial morphism. So this is indeed a member of our category. And our claim is that J kernel of phi is final in the category C. Okay, so what does that mean? Well, that means that for all pairs of objects, or all objects, which are these pairs, alpha comma p, in our category C, we have a unique morphism, alpha hat, or alpha bar, that maps p into the kernel of phi, such that diagram commutes. Okay, so this needs to be, for this to be final, this needs to be unique. And we will show that this uniqueness kind of comes from the definition, right? Because the diagram will force us to define alpha bar in a certain way that forces alpha bar to be unique. There's no other way to define it. So if we want this diagram to commute, which we do, we need for all P and P, right? So for all elements of P, we need that. So for all P and P, we need that phi composed with alpha of P. We see that for all P and P, phi composed with alpha of P is equal to 0. That's by the property of alpha P being in C. So it's a member of C. We know that phi composed with alpha of P is equal to 0 because alpha of capital P, that is a subset of the kernel of phi by definition of this being in the category. But this implies that alpha of P is in the kernel of phi for all P, right? And then we could use that, and we could take alpha bar to be just alpha, okay, with the codomain restricted to the kernel of phi. So essentially all we're doing is that we know that alpha of P, that's a subset of the kernel of phi, but really that's just a subset of M. We could just restrict alpha. Instead of having alpha map P onto M, we just restrict it and have alpha map P onto the kernel of phi. Let's write it down here. Right, so we have alpha that maps P onto M, right? And we know that alpha of P, that's contained in the kernel of phi. So really what we can do is we could just define alpha hat to map P onto the kernel of phi by taking alpha hat of P to be equal to alpha of P. So we just shrink the codomain, and that essentially is it. That forces commutativity. There's no other way to define this function, and this certainly exists because alpha of P is a subset of the kernel of phi. So there's nothing on the outside of the kernel of phi that has a preimage in P. So this is our definition of alpha bar. This makes the diagram commute, as we said, and this is the unique morphism to do so. So we see that the kernels exist in R mod through their definition, and the definition satisfies this universal property that we are after. So this is good. Now we're going to check that cokernels exist, and that the construction that we defined before, that the cokernel of phi is equal to n mod the image of phi, satisfies their appropriate universal property in the category of R modules. So as we did for kernels, we let C be a category whose objects are pairs again. So we have a pair, alpha and P. So alpha this time is going to map N onto P. So the picture that we can draw is that we have phi that's going to map M onto N, right? And we have alpha that maps N onto P. So essentially we have this. We have M onto N with phi onto P with alpha. And we have the condition, a similar condition, that alpha composed with phi is equal to the trivial morphism. So that means, as we did before, that means that phi of M, that's a subset of the kernel of alpha. Okay, so the name cokernel comes from it being kind of like a co-object. It's kind of like the quote-unquote opposite of the other of the kernel. And morphisms will be a similar construction as well. So we have a morphism from the object alpha p to the object beta comma k. In C are R module homomorphisms. So we have a diagram, alpha hat or alpha bar that maps P onto K such that the following diagram commutes, right? So we have our first object is here, our second object is here, and we have this morphism, alpha bar, that maps P into K such that the diagram commutes. What that's really saying is that alpha bar composed with alpha, well, that's going to be equal to beta, right? So if we go down through this path, that's going to be equal to going to this path. Now, the claim is that the cokernel of phi, or it should actually be written the other way around. It should be written pi, comma, cokernel phi, is initial in this category. And we're going to take pi. Pi is going to be the canonical projection, right? So essentially all we're doing here, we know that the cokernel of phi is equal to n mod the image of phi. And so all that we're doing really is taking pi, that's going to map n onto n mod the image of phi, and we note that actually in the category of R modules, when we're working with R modules, we don't have to worry about any kind of normality conditions or anything because R modules are first and foremost abelian groups. So the image of phi is defined as an abelian group. So we could just mod out by submodules, any submodule we want, and we will get a module. So n mod the image of phi is a module itself. And all we're going to do is send n and map it to its coset, n plus the image of phi. Okay, so that's the canonical projection. So we're going to claim that this is initial in C. Then what does that look like in terms of the diagrams? So that means that there's going to be a unique morphism from the cokernel comma phi, cokernel phi comma pi onto an object P alpha such that the diagram commutes, right? So essentially what we have is we have our cokernel object here, and we have another object here, and there has to exist a unique, so unique alpha bar that maps cokernel onto P. And similarly to what we did before, we're going to see that we're going to see that that the definition is forced by commutativity of the diagram. Now we know that alpha composed with phi is equal to 0 by definition of alpha. By definition of the object alpha comma p being a member of this category. So alpha composed with phi is equal to 0. And as we said before, that implies that phi of m is a submodule of the kernel of alpha, or a subset of the kernel of alpha. So this is referencing the universal property of quotients, right? If we have a submodule of a kernel, then there is a unique homomorphism, or R-module homomorphism, that maps n mod, well, I'm calling it the image of phi here, but really this is just, as we know, this is just phi of m. So n mod phi of m onto p, which is defined through this guy right here. So if we want to draw a diagram for this, we have, as we were saying, since phi of m, the image of phi, is a subset of the kernel of alpha, we have a diagram like this. So we have n that maps, we have alpha that maps n onto p, and since phi of m is a subset of the kernel, we have the projection. We have a projection from n to n mod phi of m, and there exists uniquely an alpha bar that takes our coset, m plus image of phi, onto alpha of n. This should actually be alpha of m, right? So alpha bar of m plus the image of phi, that's going to be equal to alpha of m. And we can indeed check, maybe in another video, that this is actually a this universal property exists, and it's well defined, and everything like that, and this morphism does indeed exist. And I'll just remind everyone that alpha doesn't have to be surjective, right? So this not necessarily an isomorphism, necessarily iso. It is an isomorphism, so this becomes the first isomorphism theorem when alpha is injective. I'm sorry, when alpha is surjective, this becomes the first isomorphism theorem, because yeah, because we can mod out um, by the kernel of alpha. But this does work for any submodule of the kernel. We have this this universal property, this quotient universal property, with a unique mapping from n mod, the submodule of the kernel, onto the codomain. So now we're going to prove the statement. So we're going to say phi is monic, which is short for monomorphism. So phi is a monomorphism if and only if the kernel of phi is trivial, if and only if phi is injective as a set function. So we're going to first go this way, right? So we're going to first assume that phi is monic, then we're going to assume that the kernel of phi is trivial, then we're going to assume that phi is injective as a set function, and prove that phi is monic. So that will give us the equivalence that we want. So first we're going to suppose that phi is monic, right? And we're going to consider the maps, right? So we're going to have two maps. We're going to have the kernel of phi, that's going to be the injection into M, and we're going to have I. So that's just going to be I of M. That's going to be just M. So it's the injection of the kernel of phi into M, and we have the 0 map. That's going to take kernel of phi into M. It's going to be 0 of M, not an injection. Is going to be equal to 0. So we have these two parallel maps. From these parallel maps, so we want to show that by the monomorphism property, right? If we remember, if we have two maps, alpha, that's going to map Z onto M, or alpha, comma alpha prime, that maps Z onto M. We know that if, and we have our, again, we have phi that's going to map M onto M. So we see that phi is monic if phi composed with alpha is equal to phi composed with alpha prime, implies that alpha is equal to alpha prime. So that's our monomorphism condition. And we see that this actually does hold, right? Because phi composed with the inclusion, right? So if we look at what phi composed with I of M, well, that's going to be phi of M. And we know that M is in the kernel of phi, so that's going to be equal to 0. And we see that phi of 0 of M, that's going to be equal to, well, 0 of M, that's just going to be the trivial morphism, so that's going to be phi of 0, which is equal to 0. So these do agree for all M in the kernel of phi. So that's good. So we have these maps are equal, and that implies that, so since phi is monic, that implies that I is equal to 0 by the monomorphism condition. So that implies that the inclusion map is the trivial map, but the inclusion map is necessarily an injection, right? So this is just a, so the inclusion is necessarily, so it must be the case that the kernel is trivial, since we've shown that the inclusion map is equal to the trivial map. And that can only happen when the domain is trivial. So that means the kernel of phi is trivial. So we've proven the first part. So we've proven this direction here. Now, we'll suppose that the kernel of phi is trivial. This is a standard proof. So we let A and B be in M such that their images are the same, right? And using our homomorphism condition, that implies that, so here we'll write it out, phi of A equal to phi of B. That implies that phi of A minus phi of B is equal to 0. Using our homomorphism condition, we have phi of A minus B is equal to 0. That implies that A minus B, that's in the kernel of phi, but we know that the kernel of phi is trivial, so that means that A minus B has to be equal to 0, which implies that A is equal to B. This is the standard proof that that if the kernel is trivial, then phi is an injection. So that's the standard way to go about this. Now we're going to suppose that phi is injective, and we want to show that phi is a monomorphism. So we're going to have parallel maps, right? This is the standard setup for showing something as monomorphism. We have the parallel maps, alpha that map Z onto M, and alpha prime that maps Z onto M. And we're going to suppose that this is conditions holds. That means if phi was monic, then alpha would be equal to alpha prime. So this is our goal statement. We want to show that alpha is equal to alpha prime. But we know that, what does this mean? Well, this means that for all, by this condition, that means for all elements of Z, phi composed with alpha of Z, that's equal to phi composed with alpha prime of Z. But that means that phi of alpha of Z is equal to phi of alpha prime of Z. But since phi is injective, this implies that alpha of z is equal to alpha prime of z for all z in z. So that implies that alpha is equal to alpha prime, hence phi is monic. Now, the last thing we're going to prove is the statement that phi is an epimorphism if and only if the cokernel is trivial, if and only if phi is surjective as a set function. And similar to what we did before, we're going to go this way. We're going to assume that phi is an epimorphism first. So we assume that phi is an epimorphism, and we're going to consider the parallel maps, right? So if we recall the epimorphism condition, right, that says that um, so phi that maps M onto N is epi if for all maps alpha prime that map N into Z for some object Z. This implies such that alpha composed with phi is equal to alpha prime composed with phi. That implies that alpha is equal to alpha prime. Okay, so we have this condition, and we're going to have the parallel maps, pi, that map N onto the cokernel, and the trivial map, right? So this is just the canonical projection that we were working with before, and 0 is the trivial map, the same one that we were working before. So we'll just write these down. So pi of N is going to be equal to N plus the image of phi, and 0 of M, that's going to be equal to 0. So these are our two maps. And now it's evident that pi composed with phi is equal to 0 composed with phi. Now, why is that? Well, we see that for all M in M, so pi of phi of M, well, that's going to be equal to, we're just going to project this through the projection, through the canonical projection. This is going to be phi of M plus the image of phi, but we know that phi of M, that's in the image of phi, so that implies that phi of M plus the image of phi, that's going to be equal to 0 plus the image of phi. So that's good, so that's equal to 0. And we see that 0 composed with phi applied to M, that's just going to be 0, trivially. So these guys are equal, which is what we wanted. So this implies that the since phi is an epimorphism, this implies that pi is the trivial map. So the cokernel must be trivial, and this is by the same logic. The projection mappings must be a surjection, so this forces the cokernel to be 0. Now, next we're going to suppose that the cokernel is trivial. Then n mod the image of phi is equal to 0, which implies that the image of phi is equal to n. Because the only way for this to happen is if the image of phi is equal to n. That's the only way that could happen, which implies that phi is surjective. And lastly, we're going to assume that phi is surjective as a set function. We will show that it is indeed an epimorphism. So suppose that we have two maps, alpha and alpha prime, that map n into z. Now we're gonna prove the contrapositive of the epimorphism condition. So we're going to show that if alpha is not equal to alpha prime, that implies that alpha composed with phi is not equal to alpha prime composed with phi. So we're going to have two maps that are different. So there must exist some element n in capital N such that alpha of n is equal to alpha prime of n. This is necessary because if that doesn't happen, then these are in fact the same function. Now, since phi is surjective, since phi is surjective, there exists some m in M such that phi of M is equal to n. right? So essentially what we have here is we have M, phi, and we have parallel maps alpha and alpha prime onto Z. And we know that, so we have for some, no arrow here. So for some n in n, alpha of n is not equal to alpha prime of n. And since phi is surjective, there exists an m in m such that phi of m is equal to n, okay? But this implies that alpha composed with phi of m is not equal to alpha prime composed with phi of m. Now, why is that? Well, that's simply because this actually translates to alpha of n, and we know that alpha of n is not equal to alpha prime of n by definition. So this implies that as functions, alpha composed with phi is not equal to alpha composed with alpha prime composed with phi, which that implies that phi is an epimorphism